In this video, we will develop the formula for stress and strain fields around a screw dislocation. Let us first create a screw dislocation inside a cylindrical material. So this is a block of cylindrical material. OP is the axis of the cylinder. Now I'll make a cut in this cylinder. This is a standard way of generating screw dislocation in a material. So I make a cut, a planar cut. So I'm cutting along this plane, along this horizontal plane. So O, A, B, P is a rectangular cut ending on the axis OP in my material. Let me just hatch this region so that this has been cut. Now I will slide material on one side, let us say material above this plane with respect to the material below the plane, and I will consider the sliding direction to be parallel to the axis OP of the cylinder. This will result into a configuration which I am showing here in this figure. So this was my cut plane, and now the point A has shifted to A prime. So the line OA, original line OA, has now become something like this. Original line OA becomes like that. So a ledge is created. A ledge is created here in this material. OAA prime is the ledge, and in the back also you have an overhang PBB prime, and the shift A to A prime is the magnitude of the Burgess vector. To find the Burgess vector in magnitude and direction, we will use our right hand finish to start convention, in which we take a right-handed circuit. But before that, even without making my Burgess circuit or establishing the Burgess vector, you can say that this screw dislocation is a right-handed screw dislocation. This is a right-handed RH screw dislocation. Why it is right-handed? You can see that if you curl your finger in a right-handed sense, if your fingers are curled this way, you move from A to A prime, which means if you curl your fingers, right hand finger in a clockwise fashion, the thumb points from A to A prime. This is what is the meaning of a right-handed screw dislocation. For this dislocation now, we take a T vector, let us say a T vector pointing in the material parallel to the dislocation line. Remember, T is the tangent vector and is always parallel to the dislocation line. So if I do this, then this circuit A to A prime can also act like a Burgess circuit, and in a perfect material, A and A prime would have been the same point. A and A prime would have been same point, and we would have traced a circle. But here now we are tracing one pitch or one segment of a helical path from A to A prime. So the start point A and the end point A prime. So this will be my start and this will be finish. Do not coincide, and finish to start vector, that is this vector, will act as the Burgess vector for this dislocation line. So if I introduce a coordinate system, let me introduce a coordinate system centered at O. With OA, direction OA being the x-axis. Normal to OA is my y-axis. X-axis, or let me call it the x1 axis. Normal to x1 is like x. Normal to that is x2, which is y. And then the z-axis or the x3 axis is parallel to the dislocation line. So in this configuration, you can see that the t vector is pointing in the negative z direction, whereas the b vector is in the positive z direction. T and B are anti-parallel in our RHFS convention for a right-handed screw dislocation. We can now, to get the stress and strain field, we will follow the scheme of elasticity theory, in which we have to first get the displacement field. So we will write the displacement field. From the displacement field, we will calculate the strain, and from strain we will calculate stress using equations of elasticity. So the displacement field, particularly for screw dislocation, the displacement field appears to be very simple, because you can see the displacement in going in one complete circle round the material is from A to A prime. Thus, we can write, and when the shifting or the displacement is only parallel to the x3 axis or the z axis, there is no displacement in the x1 and x2 axis. So the displacement field becomes very simple. The first displacement component u1, there is no displacement in the x-axis, u1 is 0. The second displacement u2, there is no displacement in the y-axis also, u2 is 0. So only we have displacement in the third axis direction, and that is u3. In this direction, how much is the displacement? The displacement is equal to the magnitude of the Burgess vector. But how can we write that displacement? You can see that if I go one complete circle, and now I use the angle convention, the polar angle convention, where the positive angle is from x to y. So x1 to x2. That is, I have to go anti-clockwise. So which means if I go anti-clockwise, if I start from A prime, go anti-clockwise one complete circle 2 pi, then the displacement is A to A prime, that is plus B. So I have a displacement of plus B for a complete circle of 2 pi. So at any particular position theta, the displacement will be proportional to angle theta. So if theta is 2 pi, the displacement is B. If theta is any angle less than 2 pi, it will be proportional to theta with the proportionality constant b by 2 pi. We can write this in the Cartesian coordinates because it's not difficult to relate theta, as you know. So let me do this here. If this is x1, this is x2, this is theta. So the height of this triangle is x2 and the base is x1. So tan theta is x2 by x1. So we can write theta as tan inverse x2 by x1. Theta as tan inverse x2 by x1. So we have b by 2 pi tan inverse x2 by x1. So that totally defines the displacement field. The first two components are 0. The third component is b by 2 pi tan inverse x2 by x1. Once we have the displacement field, the standard equations of elasticity for the definition of a strain will give me the strains which we'll do next. So we do the calculation for strain field from the displacement field. This is the standard equation for the strain field, where this strain ij component of the strain is simply related to the displacement field u through these differential coefficients. So del uy by del xj plus del uj by del xi added together, and half of that gives me the strain component epsilon ij. So now I can find my various components. So epsilon 1 will be del u1 by del x1, but remember we found the u1 to be 0, so this strain component is 0. Similarly, epsilon 1 2 is half of del u1 by del x2 plus del u2 by del x1, but both u1 and u2 are 0, so this is again 0. Epsilon 1 3 is half of del u1 by del x3 plus del u3 by del x1. u1 is 0, so the first term is 0. The second term will give us a strain component, half of del by del x1 of u3, and u3 was b by 2 pi tan inverse x2 by x1. So we have to differentiate this thing with respect to x1 to get the strain component. This is not very difficult differentiation to do. So b by 2 pi is a constant, comes out, so b by 4 pi. The differentiation of tan inverse gives 1 by tan inverse x is 1 by 1 plus x square. So in this case we get x2 square by x1 square. And then we differentiate x2 by x1 with respect to x1. So we get minus x2 by x1 square. If we simplify this, we can simplify all this. So we get b by 2 pi x1 square by x1 square plus x2 square minus x2 by x1 square. This gets cancelled. So we get minus b by 2 pi x2 by x1 square plus x2 square. Sometimes it is convenient to write these terms in this expression in terms of the polar variables. So let us try to do that. So I write b by 2 pi x1 square plus x2 square in polar variable is r square. So x2 by r square. But then the same quantity can now be written as x2 by r into 1 by r. x2 by r is nothing but sine theta. So I can write this as b by 2 pi r sine theta. This is epsilon 1 3. Now I need epsilon 2 2, which is del u2 by del x2. u2 is 0, so I get 0. Epsilon 2 3 is del u1 by del u2 by del x3 plus del u3 by del x2. Half of this, u2 is 0. u3 by x2 will, this u3 component is this, as you know. Now you have to differentiate with respect to x2. If you do that in the same procedure, I have gone into detail, so I leave this in the algebra. You will get simply as plus b by 2 pi r cos theta. And finally, epsilon 3 3, because it's del u3 by del x3, u3 is 0. Sorry, del u3 by del x3, u3 is not a function of x3, so epsilon 3 3 will again be 0. So we have got all the 6 independent components of the strain tensor, and so we can now write the strain tensor as the whole strain tensor matrix can now be written as 0 0 minus b by 2 pi r sine theta 0 0 plus b by 2 pi r cos theta. And since strain tensor is a symmetric matrix, 2 pi r sine theta b by 2 pi r cos theta, and this is 0. This is a simple form of the strain tensor of the screw dislocation. We will now like to convert this strain tensor into a stress tensor, and for that we have the relationships from elasticity, where all the independent stress components can be written in terms of strain components in terms of the shear modulus G, and there is another modulus lambda called the Lame's constant. Lame constant. So in terms of this, now we have calculated the strain components epsilon 1, 1, 2, 2, 3, 3, 1, 2, 1, 3 and 2, 3. All these have been calculated. So we can just substitute that and get the values of these stress components. We have seen that all the principal strain components 1, 1, 2, 2 and 3, 3, all three are 0. So if we substitute them here, since 1, 1, 2, 2 and 3, 3 all are 0, we will straight away get these stress components also equal to 0, because epsilon 1, 1 is 0, 2, 2 is 0 and 3, 3 is 0. All of these are 0. Similarly, sigma 2, 2 will be 0 and 3, 3 will be 0. Epsilon 1, 2 for sigma 1, 2, 1, 2 is still 0. So epsilon 1, 2 is 0. So this stress component also becomes 0. Epsilon 1, 3 and 2, 3 were the only non-zero strain component, and they contribute to the non-zero stresses. So all we have to do is to multiply the corresponding strain component by 2g. So you will get minus gb by 2 pi r sin theta, and sigma 2, 3 will become plus gb by 2 pi r cos theta. So the stress tensor has similar form to the strain tensor. These components are 0 and these components, the non-zero components, are gb by 2 pi r sin theta plus gb by 2 pi r cos theta, and by symmetry these have the same value. Sin theta cos theta. If you now look at the stress and strain field formulation, one thing to note is that R is coming in the denominator for both stress and strain. So this means as R tends to infinity, as we go away from dislocation, far away from dislocation, both strains epsilon ij and stress sigma ij, both of them tend to 0. So this is reasonable that this stress and strain field is due to dislocation, and as we go away from the dislocation, the stress and strain field tend to 0. But on the other end, we have this uncomfortable result that as R tends to 0, both the strain and stress components tend to infinity. So this was expected, but this is an unexpected result and is an unphysical result. Stress and strain cannot go to infinity. So this is not physical. And this is because the elasticity theory finally breaks down near the core of the dislocation. So if there is a dislocation, at this location, as we go very close to the dislocation, there is a region of radius r0, which we call core. And in the core, we cannot apply these formula. So elastic formula do not work very close to the dislocation line in a region called the core of dislocation. So this point has to be kept in mind. The core of the dislocation, the radius of the core usually is about 4 to 5 Burgess vector.